Okay, so I had to think a little bit there, original thoughts. I've never done this sort of thing before. So the solution is fairly easy once you think of it. It's still not quite dry. So you remember these residue classes behave a bit like integers. So you've got this kind of thing occurring. Alright, so what is now your set, or your group? The elements are residue class 1, 2, 3, 4. So let's find the inverse for each one. Well, what's the inverse of 1? Well, it'll just be the same, right? So it itself, the element, is its own inverse, right? So of course, that will be 1. And the unit is 1, okay? How about 2? What element gives you 1 here? Now remember it's modulus 5. So what number, now you have 4 choices, right? It's 1, 2, 3 or 4. And whatever it is, the product has got to be mod 1, or mod 5 to give you 1. So, well, try 3. Okay? So 2 3s are 6. So 6 mod 5 is 1. So that is the inverse of 2. Now if you put this in front, it comes out the same, right? So 3 by 2 is the same as 2 by 3. So 3 is the inverse of 2. So by the same logic, very similar, 2 here will be the inverse of 3. Okay? Because again that's 6. It's the same, very similar to here. Okay, how about 4? So 4, and again you have 4 choices here. What can you put here that give you mod 1? Well, if you put 1 here, you get a 4. Doesn't work. Put a 2 here, you get 3. Doesn't work. Put a 3 here, you get a 2 here. Doesn't work. So it has to be 4, right? If it's a group, it has to be. There's no other possibility. Okay, so 4 4 is a 16, mod 5 is 1. Alright? So the inverse of 1 is 1, the inverse of 2 is 3, the inverse of 3 is 2, the inverse of 4 is 4. So each element has an inverse, a unique inverse. So all 4 conditions are satisfied, and therefore this group where the binary operation is multiplied, the elements are residue classes, mod 5, with the 0 thrown out, right? That's the star here. Okay, so move on. Now here we're talking about various groups, right? Now this set here, labelled M, capital M, stands for 2 by 2 matrices, but 2 by 2 invertible matrices. Now I assume you've done enough linear algebra to know what an invertible matrix is. So if M is a matrix, an invertible matrix like this, the answer will be the unit matrix. So where all the diagonal elements of your square matrix are 1. Right? So similarly, M inverse M also is the unit matrix. I assume you know that. If you don't, you're going to have to study some linear algebra. Now I will give a course on linear algebra. But okay. Now the binary operation is just multiplication of matrices. Right? You multiply 2 matrices together, and that's your binary operation. Now they're invertible. So that means that you can find the inverse. Each matrix, 2 by 2 matrix, does have an inverse. So by invertible, so immediately for every matrix there's an inverse matrix. So immediately this is satisfied. Okay. Now what's the unit matrix? Well, it's just the the unit element. What's the unit matrix? That one, right? So just if it's an n, well, it's a 2 by 2. So a 2 by 2 matrix. So the two-dimensional unit matrix will be of this form: 1, 0, 0, 1. Okay. So it's just the unit matrix. So that's your unit. So we've got the unit, got the inverses. Now, how do you prove associativity of 2 by 2 matrices? Woo, that's not so obvious. That may be rather tedious. I won't go into that. I certainly won't do it on the board. Proving 2 by 2 matrices are associative. I think that will take a bit of work. So I'll leave that as a homework. Okay. Prove that 2 by 2 matrices that are invertible are associative. So the product of any 3 of such matrices is the same no matter how you group them, how you associate them. So I'll assume that that's done. Okay. Closed. Well, any 2 by 2 matrix, so of this form, A, B, C, D times E, F, G, H, if you multiply that out, you'll end up something of this form, X, Y, Z, G, whatever. Okay. So it's of the same. The result of multiplying 2 by 2 matrices gives you a 2 by 2 matrix. Okay. So the result is of the same form. It belongs to this set M of 2 by 2 matrices, invertible. So it's closed. Okay. So this candidate is a group. So with this set and this binary operator, the binary operator is just the multiplication of 2 groups. You take 2 groups, 2 members, and just multiply them. That's the operator, binary operator, operating on 2 matrices, 2 by 2 matrices. Okay, now the order of a group, what is that? By definition, it's the size. I'll write it out. Order of a group. Order of a group, by definition, is the group's size. The group's size. And what does that mean? That means the number of elements in a finite group. Okay, if it's a so now we can actually talk about this word here in finite group theory. Now, if a group is finite, it means its order, in other words its size, is finite. It has a finite number of elements in the group. Okay? So that's a finite group. And if the number of elements is infinite, then it's not a finite group, it becomes an infinite or infinite group. Okay? So this technical word, order, is used a lot in group theory. So the order of a group is simply its size. How many elements in the group. So pretty easy concept. Now a bit later we'll talk about the order of an element of a group, and that's a lot more subtle. So be conscious that this word order has 2 meanings, 2 uses. One is the order of the group, the whole group, and that's pretty easy. It's an easy concept. It's just its size. How many elements does the group have? And the other use of the word order, you apply the term to an element of the group. And we'll talk about that in a minute. But be conscious that there are 2 different uses of the word order within the context of group theory. There's the order of a group, and there's the order of an element of the group. Okay? So next theorem 15, which is what? Okay, so some useful properties of a group. So we'll prove another theorem. It has 4 parts. So we've got enough theory now to start proving some fairly substantial theorems in group theory. And believe me, I use the term you can build cathedrals of mathematical logic with group theory. The inherent constructibility, if you like, of group theory is just amazing. It's just jaw-dropping almost. So we're just beginning to launch along that